Thank you. My name is Ben Andrews, and I'm a volcanologist with the Department of Mineral Sciences, and I'll be speaking today about new experiments that we've been running in a brand new lab facility that helps us study pyroclastic flows. So you may ask yourself, what is a pyroclastic flow? And here's a picture of one from Cinnabung volcano, which was erupting very recently. This is a picture from about 3 months ago. And you can see this pyroclastic flow here. It's a very nasty cloud of fast, hot, and dense pumice, ash, and gas. It's several hundred meters thick. Those are trees there for scale on the edge of the deposit. It's moving very quickly, probably about 50 miles per hour or thereabouts, and it's exceptionally hot. That current is probably about 400 or 500 degrees C. So as a result, these currents pose substantial threats to, or substantial hazards to life and property. Pyroclastic flows such as this one can easily travel 5 or 10 kilometers, and really big eruptions such as things from Yellowstone or smaller eruptions like Krakatoa can send pyroclastic flows many tens of kilometers. So they pose very great hazard, and they also can threaten aviation because these pyroclastic flows can also make buoyant plumes that throw ash up into the stratosphere where airplanes fly. And as a result, pyroclastic flows can threaten aviation many thousands of kilometers away. And so our basic questions then we can think about with pyroclastic flows are: how far will a current travel? How fast will that current go? How big will the current be? And also, where will that current go? And you can think about this with that map there of the Naples area in Italy. So we have Mount Vesuvius, very prominent in the middle, the city of Naples all around the bay there, and then the Campi Flegrei system of calderas, which is on the left side there. And these volcanoes have erupted in the past, and they will erupt again. And we would very much like to know, where will the pyroclastic flows from these eruptions go? Will they travel across the bay? And the answer is they very well could. And how will they be affected by topography? One of our problems, though, is that much of our understanding of pyroclastic flows is based upon simple two-dimensional models of turbidity currents, so cold currents, and there's no real accounting for air expansion in these models. And as you'll see in the next couple slides, air expansion has a huge effect on the dynamics of these currents. So we built a new laboratory out at the Museum Support Center in Suitland, and we ran our first experiments in May. You can see the lab taking shape here. It's about 28 feet long, 20 feet across, and the interior space here is 8.5 feet tall. So this provides a unique facility in the world for studying unconfined systems, unconfined pyroclastic density currents, or pyroclastic flows. And this is a cartoon of what that lab looks like. So the way that we make a pyroclastic flow in the lab is we load powder onto a conveyor belt shown coming in through that hole on the upper right. The powder then gets fed at a controlled rate down a chute in that big gray box, and then it flows out across the floor as a dilute cloud of dust. And we can illuminate these dust clouds, or these model pyroclastic flows, with orthogonal laser sheets shown there in the red, green, and blue. And you may ask yourself, how are we able to use a small laboratory setting with dust to study very nasty pyroclastic flows? And without getting into too many details, the answer is that we can balance the forces. And so those natural currents might be 1,000 meters thick, moving at 100 meters per second and 500 degrees C. We can balance our currents down so that our currents are maybe 20 centimeters thick, moving at 30 centimeters per second, and they're 1 degree warmer than the room. So not very nasty, but they shed a lot of light on how the natural systems work. So here is an example of one of these currents. And right here, we'll see a cold current coming in. It's been sped up by a factor of 5. You can see it spreading out radially out across the floor. So it's essentially spreading equally in all directions until it starts to hit the wall there on the left side. And in a moment, it'll hit the wall at the end. And we can see that these cold currents essentially behave just like our cartoon understanding would suggest. There's a well-developed current head that we'll see coming in again, a well-developed current head followed by the body, and there's a lot of mixing and air entrainment going along on the top of this current, but because the current is cold, that mixing doesn't have any big effect on how the current behaves. Now if we look at a warm current that's otherwise the same as the previous one, but this time it's warm, we see big differences in behavior. So this guy comes in, and now we see very vigorous mixing on the left side of the current and also on the right side. There's a buoyant plume is lifting off, so this would be causing a threat to aviation. We see, if it were a real current, we see the total runout distance is very much reduced. We're no longer flowing down the length of the tank. Instead, we're now only going about 12 feet out. And we can see that there's a very different behavior then. So the previous current had radial behavior, radial spread, and this guy is very much focused behavior and very limited runout. So if we think about this, then we can see that the three-dimensional structures are very much controlling pyroclastic flow behavior. Air entrainment is controlling how these currents move, specifically air entrainment and expansion, and that air entrainment and expansion evolves through time. So if we start with our 2D model that we have here, we can rotate that into 3 dimensions, and that works pretty well for a cold current. We have a lot of entrainment on the back of the head and some on the top of the current, but things behave radially. On the other hand, if we have a buoyant plume start to form, so if our current is warm and it expands and lifts off, that upward rise of a plume changes the current behavior, and now the air entrainment is focused on the sides of the current. The current or the pyroclastic flow can no longer spread radially. Instead, it stays very much focused. So to wrap this all up, we're getting new insights in this facility that we could not have gotten really any other way, and we're developing predictive models for flow behavior that allow us to better understand how far currents go, how they interact with topography, how their deposits form, and a whole lot of other wonderful things. Thank you. The question is, how will we test our predictions against real data? And that's a very good question. And the answer is by looking at deposits from modern and ancient currents. So we can look at deposits from, say, Mount St. Helens or Cinnabung volcano in that picture, and we can look and see how far those currents went and how those pyroclastic flows behaved and compare them with our predictive models. And then for the really big eruptions like Yellowstone size events, we just look at the deposits, and no one was around, so there's no real direct records of those, but we can make get a pretty good idea of how those currents behaved. Thank you.